Hello everyone. Welcome again to Discrete Mathematics and its applications with me, Adila Krishnadi. We are continuing the previous video where we discussed set operations on binary relation. Now we look at another operation of binary relation, namely the inverse operation. So the intuitive idea of inverse is that if you have a relation R, then its inverse is simply the relation in the opposite direction. So to be more formal, this is defined this way. So if you have R, a binary relation on A and B, so from set A to set B, then the inverse of R, which we denote by R to the power of -1, so this is the inverse of R. It is a binary relation from B to A. So note here that if you have R from A to B, then inverse of R must be from B to A. And this is defined simply as, well, a set of pairs of B comma A if such that A comma B is in R. Yeah. So that means if you have A in A comma B in R, then B comma A must be in the inverse of R. Now, if you recall the definition of the symmetric property of binary relation, then you see there is some similarity with inverse operation. Yeah. So inverse operations deals with the relation in the opposite direction as well. However, there is a subtle difference here. Symmetric property holds when when the relation contains both A comma B and B comma A. So that is, if you have a relation from one direction, then the opposite must also be in the relation. Then if this holds, then the relation is symmetric, if this holds for every pair. Now with respect to inverse, you don't actually test, or you don't actually look whether something holds, but rather you have a relation, you get another relation, and in this case you have R, then you get another relation that you call the inverse of R. So it is different. Now to see the difference, let's see some examples. Or before that, let me just draw a few pictures here. So in symmetric property, if you have a relation here like that, then this is R, then the opposite must also hold. So the opposite must also be in R, right? Whereas in inverse, if you have a relation from A to B, this is A, this is B. If this is related by R, then the inverse would contain this. So that's the idea, right? So how do we get an inverse from of a relation? Well, you simply flip the pairs for every pair there. So let's have a look at some examples. So here you have two binary relations, R1 and R2, defined on A, where A contains the integers 1, 2, 3, and 4, and R1 and R2 are defined there. Then what are the inverse of R1 and inverse of R2? Well, this is pretty easy. If you see R1, inverse of R1, then you just take all pairs of R1 and flip each of them one by one. Now let's have a look. So you have 1 comma 1, you flip, then you have 1 comma 1. 2 comma 2 is flipped into, again, 2 comma 2, and 3 comma 3 is flipped, you get 3 comma 3. So like this, right? So you have here, then this is R, and then therefore the inverse must be in R1. So, right, this is R1, this is R1, this is inverse of R1. So it is possible, like here, that actually the inverse of a relation is the same as the relation itself. Now how about R2? So you have your R2, Then the inverse of R2 is you take the pairs. So for example, 1 comma 1, and you flip the direction, then you get 1 comma 1 right here. Now how about 1 comma 2, right? Then you flip it, then you get 2 comma 1, right? So therefore 2 comma 1 is here. And similarly, you have 3 comma 1 and 4 comma 1, right? So this is the inverse of R2. Now in R2, the inverse of R2 is not the same as R2. Yeah, so it's clear. So this is pretty easy. So let's do some exercise. You have this relation R1 and R2, where R1 is defined such that B is greater than A, and R2 is defined such that B is equal to the floor of A. So this is floor of A, that is the largest integer that is less than or equal to A. So remember, A is a real number, and the floor of A, which is B here, is an integer. So let's do this, and we shall discuss the solution in the next video.